Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jihye Hwang with us today. Hey, Jihye.
Hello.
Thank you very much for agreeing to talk about your very lovely article.
Thank you for inviting me.
Pleasure. And what is your, where are you located at?
I'm located in Daejeon, the middle of South Korea. I'm working in Korea Astronomy and Space Science Institute at Kashi.
Cool. Very cool. So we're going halfway around the world today for this one. So very nice. Is it spring in Daejeon, South Korea, or is it?
Yeah, it is spring.
You got your flowers.
It is good weather. Yeah, clear sky and
yay.
good temperature. Yeah.
Good. Very cool. Very nice. It is, well, it's my May 11th. It's Jihye's May 12th as we record this. And it is springtime coming into summer in Phoenix. So all of our flowers have done their bloom and are coming back down. So very soon the power switch will get thrown and it will be very warm here in Phoenix as we go.
Yeah.
And Jihye, what do you like to do for research?
I'm interested in star formation. So especially I have focused on the role of magnetic fields in star formation. So I usually use the polarization data obtained by the JCMT, James Clerk Maxwell Telescope. And I would like to extend my work to use interferometry data to show the details magnetic fields within the cloud.
Cool. Very nice.
Yeah.
And that is going to bring us to this very awesome AJ article. So number one, it's open access, people. You can go get a copy for free. We're in the open access era. Magnetic fields in the Horsehead Nebula. And Jihye, take us away.
Yeah. This paper aims to study the role of magnetic field in the Horsehead Nebula. So the data of Horsehead Nebula is obtained by Malarigo using the JCMT. She is a high school student and she is awarded time under Mauna Kea Scala program.
That's
and
great.
I was supported by the UST overseas training program. So I did this work in the UK with Kate Potter.
Okay.
And so I would like to appreciate two programs to conduct this work.
Very nice.
So, let's start to summarize my paper.
Okay.
The Horsehead Nebula is a famous astronomical object, as you know. Indeed. It is a well-known PDR, photo dissociation region. The PDR is generated by strong UV radiation from massive stars. The radiation ionizes parental molecular clouds and makes H2 region. And the expanding H2 regions makes the compressed neutral gas structures. So PDR usually shows elongated structure or shell-like structures. Okay. And magnetic fields in PDR can support their overall structures, but there are few studies about the magnetic field in these regions.
Yeah, right.
And especially the Horsehead Nebula is located at close distance, so we can see the detailed structure within there. It has been made by UV radiation emitted from a massive star, Sigma Orionis. And the previous submillimeter studies have shown there are all starry core and PDR together in the Horsehead Nebula. Okay. So we can discuss magnetic fields in the PDR, also in the starry core. And magnetic fields has been studied using dust polarized emission. The dust grains are spinning by radiative torque and aligned along magnetic field lines. Okay. So if we observe this region at optical and near infrared wavelengths, the starlight will be observed by aligned dust grains. So the polarized light will be aligned along magnetic field. However, if we see dust polarized emission from the aligned dust grains, the polarized light is perpendicular to the magnetic field lines. So by rotating the polarized light by 90 degrees, we can see magnetic field orientation. So in figure one,
figure one, and
we can
figure one.
Yeah. So in figure one, the black segment is obtained at sub-millimeter wavelength using the JCMT, and orange segment is obtained at optical wavelength, and they shows magnetic field orientation. In case of optical wavelengths, we cannot see densest parts the magnetic fields because the high extension of starlight. And the background image is obtained by Hubble Space Telescope. It looks like Horsehead, so it is the Horsehead Nebula. And figure two.
Well, figure two, let's think. We got some data reduction. And figure two, okay, here we go.
In figure two, we also show magnetic field orientations in the Horsehead Nebula. The background image, the dust continuum at sub 850 micrometer, and the light source is named as SMM1 is the PDR region, and the left source is the starless code named as SMM2.
Okay.
Polarization segments, red polarization segments are obtained by the JCMT, and they choose well-organized structure overall. So it means magnetic field is quite important in this region, and the green segment is obtained by Planck data. It is the same wavelength with the JCMT. However, the beam size is 10 arc mini. It is much larger than the JCMT.
Right.
Yeah, but overall, we can see overall magnetic field orientations in this region, and
very cool.
blue contrast is obtained by the Palomar Observatory at optical wavelengths, so we can see diffuse particles magnetic fields in H2 regions. So we analyzed the overall orientations of magnetic fields in figure 4. I will skip figure 3.
Okay, so we will go from scuba plot to, then we got our polarization vectors and our polarization analysis, some of our results, and magnetic field orientations. There we go.
So I showed the magnetic field orientations using a polar chart. And magnetic field orientation are usually measured from north to east directions. So the left panel shows the polarization magnetic angles from north to east directions, and due to the 180 degrees ambiguity when we decide polarization angles, we can see actual vector directions. So we can address the Palomar Observatory and Planck Observatory data from 180 to 360 degrees. It is agree with each other, the opposite directions from left side and right side. So we can show the magnetic fields in SMM2. So the starless score are well matched with Planck observations each other and slightly different with the Palomar Observatory. But in case of the magnetic field orientation in SMM1 PDL region, they are widely spread, and we can see a mean direction. It is because the magnetic field orientations are perpendicular to the curved PDL regions oriented.
Okay.
And so, but we can see magnetic field is well organized in these regions, but to discuss the importance of magnetic fields in this region, we have to estimate magnetic field strengths. So magnetic field strengths have been usually estimated using the Davis-Chandrasekhar Fermi method.
Okay.
In the method, the main assumption in the method, the magnetic field is has uniform directions, and they are distorted by non-thermal gas motions. But in actual world, magnetic field lines are not uniform direction, and it can be curved or tangled by other gas motions or gravitational force or import outflow, something like that. So Hildebrand et al. Suggested a method to separate the ordered and turbulent components.
Okay.
So we can see in equation 6.
Equation 6. Let's do that one.
And 6 and 7.
Let's go down to 5.
Down.
Column density 6 and 7. There we go. Angular dispersion.
Yeah. Angular dispersion. So they suggested the angular dispersion method to separate ordered and turbulent components of magnetic fields in equation 7. B is turbulent component and M is ordered component. So if we fit in this equation, we can obtain the turbulent component and we can estimate magnetic field strengths. So the equation of the D-shape method is shown in equation A. In the method, we obtained turbulent component from the angular dispersion function, and we decide density and velocity dispersion. We can derive magnetic field strengths.
Right.
So
okay.
In figure 5, we can show the fitting result of angular dispersion function.
Yes, figure 5. Here's our angular dispersions. There we go. Or the PDF and the core. Yep.
Yeah, so we fitted the angular dispersion function and obtained the turbulent components and estimated magnetic field strengths. So from the estimated magnetic field strengths, we also estimated mass to flux ratios and Alpha-band Mach number in SMM1 and SMM2 to investigate the relative importance between magnetic field, gravity, and turbulence.
Cool. Okay.
So mass to flux ratios is shows the relative importance between magnetic field and gravity. In both the sources, we can show they are sub-Alpha-band. It means magnetic fields are sufficiently strong to support their structure against the gravitational collapse.
Okay.
And we also estimated the Alpha-band Mach number. Both the sources are sub-Alpha-band, so magnetic pressure is more dominant than turbulent pressure. It means in both sources, magnetic field is much dominant compared to turbulence and gravity. And in case of SMM2 Starry's core, we additionally obtained the magnetic, turbulent, and gravitational energies. And it is also shown magnetic energy is the largest value, although we consider uncertainties or number of eddies, something like that.
Okay.
And despite of the large magnetic energy, star's core is not expanding, and they are containing their structure.
Yeah.
So we proposed two hypotheses. One is the overestimation of magnetic field strength.
Yeah.
Usually in the DCF method, magnetic field strength can be overestimated by a factor of 3 to 5. Then it means magnetic energy also can be overestimated. And second hypothesis is external pressure can contribute to the energy balance of starless core. So, example, the mass flows along pillars. So, embedded starless core can be affected by external pressure from the gas motion.
Okay, cool. Very nice.
And from these magnetic field orientation and strengths, we made a schematic view of the Horsehead Nebula in Figure 6.
Figure 6, mass to light flake. So energy balances is what we just talked about. Energy balances. And there we go. Figure 6. Schematic of the Horsehead. Okay.
Yeah. Build gray lines is the mean magnetic field orientation in H2 region obtained by Paloma Observatory, and the red lines shows magnetic field orientation obtained by the JCMT. And we can see Sigma Orionis upper right corner as a blue star. Yes, this is the radiation from this star will make these pillar structures.
Cool.
The starless magnetic field orientation in starless cores are not matched with pillar directions, and it is slightly different with the H2 magnetic field orientations in H2 region. So we assumed that the starless core is made before pillar and can be affected pre-shocked magnetic field orientations.
Okay.
Yeah. And in case of SMM1, the PDL magnetic field lines are perpendicular to the PDL structures.
Yes.
And in numerical simulation, magnetic field lines can be aligned along pillar structures, and at the edge of the pillar, magnetic field lines show a hairpin structure, covered structure, but we cannot see the covered hairpin structure. So we suggested two reasons why we cannot see the hairpin structures. First, the hairpin field lines are ported back to the PDR structure. So we can see the frontal part, so it can be perpendicular to the overall structure. Second, the pillar is slightly inclined with respect to the plane of the sky, and we can see like this. We can see the projected lines perpendicular to the structure. So
cool. Very cool.
Yeah, that's our schematic view of this region. And in summary, we observed the magnetic field in Horsehead Nebula, and we estimated magnetic field strengths and other parameters to discuss the role of magnetic fields in SMM1 and SMM2. Both sources show strong magnetic fields compared to turbulence and gravity. So in conclusion, magnetic field plays an important role to form and support the Horsehead Nebula. So that's all. Thank you.
Very cool. Jihye, thank you so much. Thank you so much
Thank you.
for walking us through your very lovely article. Very good. And you mentioned it a little bit at times in your talk, and I'll push on it a little bit. So where do you think we go with this topic over, let's say, the next 2 to 5 years? Are there going to be additional observations from the Maxwell telescope? Are there other telescopes that have polarizers that we can use it? Is there some theoretical work that can be done? So where do we go with this on improving our knowledge about the magnetic field of the Horsehead Nebula?
So I'm working as part of a Bistro project prepared in star forming regions observations.
Okay, cool.
So it is a large program of the James Clerk Maxwell telescope, JCMT. So we observed a lot of fields.
Right.
To study magnetic fields. So I'm working in another sources. So I'm also interested in the PDR regions. There, as I mentioned first, there are a few study of magnetic fields in the PDR. So I think within several years, we needed to observe and publish the study about magnetic fields in PDR.
Cool. Great. Very good. Well, I certainly look forward to seeing the new data come out, and we'll learn a little bit more about the Horsehead Nebula. It'll be wonderful. Jihye, thank you so much. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.